Welcome back from the coffee break. I'm going to take just 1 minute to do a couple of administrative things. We're starting the sessions. During the sessions, I have the distinct honor today to remind you to get going with your presentations. So I'm going to have 3 colors here, okay? So if you see green, you have 10 minutes left. If you see yellow, you have 5 minutes left. And then on red, it's over, okay? We're going to be very aggressive because we have a long day ahead of us. So if you want to have a 10-minute Q&A, then you're done on green. If you have a 5-minute Q&A, it's kind of up to you. It's your build your own adventure. Also, when you do ask questions, maybe mention your name real quick. Then we have that on record, and people that watch us afterwards kind of know who you are. Unless you're very famous, then people know who you are anyways. So I leave that up to you to decide whether you think you're famous or not. I think with that being said, I just want to say real quick, thank you for the Harrington Foundation one more time. When I learned about it, I thought to myself, who would be crazy enough to just uproot their life and move here for a year? And I texted Adrian and said, hey, Adrian, would you just uproot your life and move here for a year? And he said, sure. So that was very easy. And we wrote this application together. He's been here, and it's been a real dream. We got our PhDs together 15 years ago or so. And having him here was just a fantastic academic, but mostly friend-based experience, and we're really sad to see him leave. With all that being said, I guess we get back to the program. He's replacing Alan, who unfortunately couldn't be here, but being Alan's trainee, I think he's going to be the best replacement for her we could hope for. He's going to be speaking about data-driven inversion of full-field deformation data with null ordinary differential equation fields. It's a fantastic title. You're perfect. With that being said, you have about now 28 minutes. I did that to you. All right. And then you know the color game. All right. Thank you much.
All right. Thank you. And yeah, you get me instead of Ellen. I'll go a little bit into more of the machine learning side of things, but I do want to motivate a little bit of what we do. And we aspire to do some digital twins. We are not really at the level of what Ken was presenting in the previous slide, but this is sort of similar vision to what in my lab we are trying to do, is building predictive models that interact with clinical data of patients in order to improve decision-making in the clinical setting. And so we have been getting data from different systems, both in the clinical setting, but also from animal models, like pig experiments, murine experiments, and then combine that with biophysics models that encode our knowledge about the physics and the biology. We do want to be mindful of the fact that there's uncertainty, a lot of uncertainty in these systems, particularly from the biological side. So a lot of the things that we try to do is building these probability distributions over the population, so that when we get some data, maybe not as much data as we would want, but just a little bit of data from a patient, we can get that instance of that personalized model that really leverages all that previous both physics models and the previous data across maybe multiple species. Some of the example applications that we work on a lot are breast reconstruction for breast cancer. So these are 2 examples of the types of simulations that we do. I'm not really going to talk about that much today, but just to give you an idea of, at the end of the day, what is our end game? What do we want to do? We want to make predictive models, for example, of breast conserving surgery for treating breast cancer, and we would like to predict the healing outcomes over weeks to months after the procedure. Also for mastectomy or total breast removal, we create finite element models to basically predict what the shape of the breast after tissue expansion would be, and the simulation that you're seeing there is after calibrating to longitudinal 3D photography. And we do pretty well in the error, for example, with respect to predictions and the actual clinical geometries. Sort of what I want to talk about today is a little bit more on the nitty-gritty of the methods. So in that sense, I will switch gears. So we have these processes that we care about, for example, the tissue expansion surgery, wound healing, and then we build these biomechanics and mechanobiology, mathematical and computational models. We do a lot of machine learning-enabled model calibration. That way we can, and especially we've done a lot of Gaussian process surrogates to try to keep track of that uncertainty. And what I'll talk about today is mostly how do we get rid of that mathematical and we go fully data-driven. So for that, we use neural ODEs, is one of the sort of keywords in my title. And we do this to represent material models with automatic polyconvexity. So the challenge that we're trying to address is, can we code physics constraints directly and instead of through loss functions? And so the challenge is that we want that to be automatically. And we use neural ODEs to construct automatically polyconvex material models. And this is important because it gives you some guarantees about existence of minimizers for the boundary value problem. The reason why this works is because the neural ODEs map invariance to monotonic derivative functions. I'll explain that in a little bit more detail later on, but this is sort of our training framework. We have some data, typically in the form of stress-strain curves. We process that to get invariance, so we satisfy some things like objectivity. Then our prediction is, there's different approaches in the field. What we do is we predict derivatives of the strain energy, and the reason why we focus on the derivatives of the strain energy is because that's directly what you need to assemble together to put the stress tensor. So you don't really need the energy, but just the derivatives. And then we have a training loss. And so importantly, there's no penalty that takes any sort of physics constraint. It's embedded in this neural ODE framework. And a neural ODE is basically the continuous version of a recurrent neural network, is basically the right-hand side of a differential equation. And this is what we use to map invariance. So I don't think this works very well. But we basically take the invariance of the deformation as initial conditions, and then when we pass them through this neural ODE, we get these derivatives of the strain energy. What is the polyconvexity requirement? Like I said, it's not a necessary, but it's a sufficient condition to get solutions of boundary value problems. So that's why it's desirable. It's that you have a convex function in the extended domain of the deformation gradient, the cofactor, and the determinant. Generally, enough family of functions is the sum of a convex function in f, a convex function in the cofactor of f, and a convex function in the determinant of f. And you can think of this as energies that penalize changes in length, changes in area, and changes in volume. Instead of working directly with f and the cofactor of f or the determinant, we work with the invariance of the Raj-Cauchy-Green deformation tensor, your usual invariance. And then because the invariants are themselves quadratic functions of either f or cofactor of f, then these functions have to be convex and non-decreasing. Our general expansion of the energy looks like this. So we have a sum of individual scalar energies of the different invariants, and then we also do sum of convex combinations of pairs of invariants, just to give enough flexibility to cover arbitrary materials. And even though our expansion of the energy is the one at the top, like I said, what we actually capture is not the energy itself, but the derivatives of the energy. So really what the neural ODEs prescribe are basically these trajectories of the derivatives. I'll let this play a little bit. There's going to be some text. It's going to be very quick. So get set on your mind. I don't know what the counting is in English, but go. All right. Hopefully you had time to read what came up on the screen. But basically, the neural ODE is a vector field on the left side that allows you to map these invariants to these derivative functions. You get monotonic derivative functions, which means that the underlying function is convex. And this gives you automatic polyconvexity by default. So if you have training data that is convex, this is the GOH material model, and we train with just the quarter on the right, then the predictions are pretty good. However, you can create material models that violate this polyconvexity condition. So the fung with particular parameters, you can make it be non-convex. But if you train our architecture, there's no way that you can get a non-convex function. So it is by default. And it's flexible enough that it really reconstructs this is actual experimental data from porcine skin, and it reconstructs the data better than all the other models. So we train with a subset of the data, and we test with another subset of the data. And then the model are these surfaces. So these are 4 different models that people use for modeling soft tissue. The GOH or HGO is just whether or not it has a fiber distribution or not. The Mooney-Rivlin, the Fung model, and our NODE model. And you can see that some of the most popular considered models for soft tissues, these GOH or HGO, have this exponential function. And therefore, once you get outside of the training region, you'd really get this exponential increase. So if you think about propagation of uncertainty and evaluating outside of the region where you trained, then you can predict really incorrect stresses. Whereas the NODE, one of the features that happens because we do a neural ODE on the derivatives is that they tend to go to a constant value, so basically a stable point of the differential equation, and that would mean basically constant stiffness after a while. So you might get this initially exponential increase, but then it will become constant. We've applied that in Abacus. We had to code in Fortran basically the neural network architecture. So that's one part of the title. The other part of the title is generative models, because we want to include some sort of sampling of uncertainty. And what I showed before is basically we can fit a single sample. And now, what if we want to fit a family of materials? And so what we use is generative models with score matching. So this is the type of model that generates these pictures when you put a text prompt that you want. These are the ones that I had in the original slide for different images of skin surgery. So basically what you do is you have some distribution that you want to infer, so this P of phi naught. And then you don't really have the distribution, but you might have samples from it. But you can define this process that basically gradually destroys that data and turns it into an uncorrelated noise or a standard normal distribution. And you can actually analytically get the distributions in between the original distribution as you gradually turn it into the standard normal. And you can go back. So you can start from sampling on the standard normal, and then the stochastic differential equation that you need to solve looks like this, where the key thing is this forcing term that basically takes you along the gradient of increasing probability. So this gradient of the log probability, this is the score function. This is what you're trying to learn. And this is basically the forcing term that from these samples of the uncorrelated or from the standard normal, it will push you into the directions of greater probability. And you can estimate that by minimizing a mean that you estimate with the samples from P of phi naught. So you don't actually have P of phi naught, but you have samples from it, so you can estimate these expectations over this trajectory. So this is the empirical approximation of that distribution. And so what you can do with this is that you have some mice, and you have some stress-strain data, and we want to learn what is the probability over these psi or strain energies. In reality, what we do is we parameterize this with the neural ODEs, where some of the parameters are constant and some of them are sample-specific. So the orange ones are mouse-specific. And then the question then, instead of trying to infer a probability distribution over the strain energies, we learn the probability distribution over the parameters of the NODEs. And we do that with the score matching. So we corrupt the data with noise, and then we go back from the standard normal back to the correlated data by learning that score function, the S sub theta. And so when you do that, then you can generate new material models. You're basically generating new NODE that give you sort of new mice that should be within that distribution. And one of the things that we found out with this algorithm is that it works really well for this very weird type of correlation between the neural ODE parameters. And so it really does much better than standard density estimation techniques, so like kernel density estimation techniques. And this is because the correlations between the weights of the neural ODE, this orange band, are super non-Gaussian. So if you are trying to fit this with some family of like mixture of Gaussians, then you really cannot do it well. But the score matching does really well with this type of non-Gaussian correlations. And this is sort of the actual data. So the orange ones are actual mice that were tested in Manuel Rausch's group, and then the gray ones are ones that we generate after training this generative model on the NODE parameters. And we've extended this to sample not just material distributions, but heterogeneous materials. So instead of sampling from a standard normal, one thing that we can do is sample from a Gaussian process. So instead of just a particular point in space, we can sample from a correlated set of Gaussians. So here you have the x coordinate, and we can sample. If you take a slice, it looks like the slices that I was showing you before. So it looks like uncorrelated noise. But if you look over x, then you have some smoothness that is determined by whatever you put in the kernel. So if your kernel is some exponential kernel, then you with a large length scale, then you will get very smooth correlations on the x coordinate. And so what we solve is you can select the kernel such that indeed if for a slice you do have a standard normal distribution. So we do that. And then, yeah, like I say, you can control things like the length scale. And so when we pass that through the reverse SDE, then we get NODE parameters. And again, you have both, you have the correlations of the different NODE parameters that you had even in the previous slides. But now also you have a correlation across the length variable x. And so you can do that to generate, for example, a heterogeneous response. Even if you have the same deformation applied to the entire system, you can get stress that varies over x. Because when you sample, again, when you sample these NODEs, you get NODEs that change both because of the individual samples, but also because they change along a particular spatial dimension. So one thing that we've use this for is to sample then on some uncertainty of these material distributions. Soft tissues tend to be heterogeneous with noisy material distributions, so these are changing the different length scales. In this case, for example, because we don't really have any information about the correlation spatially, these are all Gaussian at the end, so there's no really coupling in the space. So it's not trained. So we start with a Gaussian process, and whatever spatial correlation we bake in at the beginning, that's basically what we end up at the end. So in this case, these are all samples from a Gaussian process, basically. But now they are correlated in terms of the parameters. We can also do this in complex geometries. So this is for the Purdue P, where you can basically solve the eigenvalues of the Laplace-Beltrami operator, and that gives you a basis to then construct which these you can do with standard linear finite elements. And then once you solve those eigenvectors, then you can construct a kernel over arbitrary geometries. So typically, the other kernels that I was showing you before in the square domain, those are well-defined for these square problems. But if you want to sample on arbitrary geometries, then you can do this with these eigenfunctions of the Laplace-Beltrami operator. And so with that, you can get samples that are, again, spatially correlated over arbitrary geometries. And then for the last little bit, I'll talk about the inverse problem part. So one of the problems that we're interested in, so in the forward problem, you typically have some material properties, and then you predict some strain and boundary conditions. And in the inverse problem, if you have, say, for example, DIC data, you go from strain and boundary conditions, and you want to go back to a stress field and a set of material properties. And you would like to impose, the thing that connects the material properties and the stress field to the strain and boundary conditions are the physics. So you want to satisfy equilibrium, either in the strong or the weak form, either the divergence of the Piola stress to be 0, or the integral of the Piola stress with the variation of f to be 0. And there's a lot of methods that you can use for inverse problems. There's Bayesian methods. in which case you would just sample repeatedly the forward problem, maybe replace it with a surrogate. There's virtual fields methods, which yields a system of equations that can be solved in the least square sense. Some common assumptions in the literature is that the material model, this stress as a function of f, is assumed from a library. And also there's some restrictions on what is the spatial distribution of these material properties. And so what we wanted to do was to do this type of inverse problem, but for arbitrary materials, in particular based on this NODE that I was showing you before. And can we do it for arbitrary continuous material fields? So no restriction on single material or at most two materials, but arbitrary parentheses continuous. And so I'll just show you the results with the experimental data set in the interest of time. Basically, we have there's the MNIST data set that you might be familiar with from computer science. And we've 3D printed these samples. Well, Manuel has 3D printed these samples, tested them, also tested the homogeneous materials, and then speckled them and captured the images and got the DIC displacement field data. And what we do is we have this DIC data, and first of all, we replace the displacement fields with a continuous representation by using a neural network with Fourier features for the X and Y components. And with this, we have now a continuous representation of this displacement field with high resolution. And the reason why we want that is because we want to take derivatives to get the deformation gradient. So this is what the experimental data looks like. We learned basically these displacement fields with a neural network with these Fourier features, and that does a little bit of denoising for us. And then we can take derivatives, so we can do autograd in JAX to get the gradient of the displacement field to get us our deformation gradient, and then we put that deformation gradient into we have a hypernetwork, so the initial part is this really doesn't work. But the top part is what I showed in the last slide. We have the displacement field, we feed a neural network, we take the derivative, and then we train a hypernetwork that tries to predict a neural ODE for every spatial location. So the hypernetwork just takes the X and Y locations, and it will predict an NODE for that XY location. And then we take the invariance from the DIC data, we evaluate the NODE material, we get the stress, and we check whether or not that satisfies equilibrium. And so our loss function is essentially the equilibrium and the boundary conditions. And our trainable parameters is the hypernetwork. So not even the NODE, but the hypernetwork that produces the NODEs. This is what our predictions look like compared to the experiments. It's not perfect. I have to say there's some noise in the data, and maybe you can do better. And it's okay. It works really well with the synthetic examples. I mean, it's perfect with synthetic examples when you don't put noise. But if you think you can do better, we have a challenge for you. That we'll be posting soon. So Emma, who's here, has developed a mechanical MNIST benchmark data set. And this one is synthetic as well. And so one thing that we wanted to do is add on to that and build a physical MNIST data set. And so we've 3D printed, I think it's 100 samples that look like that. And then we've done tests similar to what I used in the problem, gotten DIC data and boundary data. And so we'll be posing a couple of challenges. One is going to be an operator learner or forward problem to predict force displacement curves based on the and full field deformation data from the geometry samples. So if you give you what the MNIST file is, then and just tell you the labels of the materials for you to predict the DIC results, basically. And the training set will be 90 out of those 100. And then the data includes the force displacement over time, the full field strain maps, and the metadata, so basically the labels of the geometries. And then we'll be testing your results on 5 in-distribution MNIST samples, 5 out-of-distribution non-MNIST samples, and 5 homogeneous material samples. And we'll also be posing an inverse problem where the goal will be to, again, just take the DIC and force boundary data and get us back the material properties and the geometry. And with that, I'll finish. So conclusions, data-driven methods can be used for model individual material response better than closed-form models and satisfy physics such as the polyconvexity constraint a priori. Diffusion generative models can be used to estimate the probability density of a family of materials. And heterogeneous data-driven materials can be inversely identified from full field data with a hypernetwork approach. That's it.
Alrighty, we have about 5 minutes for questions. Just a quick reminder, if you have a question, I'll hand you the microphone. Just say your name real quick. Any questions? Oh, easy enough. Boardwalk.
If you print a sample, right, you the multi-materials, right, if they have different Poisson ratio, and if you add a loading condition, they might also have different out-of-plane deformation. Are you to look at the 2D or 3D DIC?
This is 2D DIC. I don't know if the DIC that we've processed is 2D DIC. I don't know if we have 3D information.
We only collected one image set. I'll come all the way over there with my athleticism and my Birkenstocks. There you go.
Following up on that data set, I'm a big fan of this mechanical MNIST data set, actually. I'm presenting it tomorrow as well. So how are you actually controlling the Young's modulus and all the properties when you're 3D printing the material?
This is a little bit more of a question for Manuel. So I don't know what the recipe are. We had a few choices of 3 materials, no?
Yeah, so we use a Stratasys printer that basically has a technology to co-print different materials, so you can continuously vary the stiffness of the material. Yeah, but we chose 5 different material sort of settings. We have homogeneous samples, and that data is being used depending on which challenge you participate in to calibrate or to test.
And yeah, the things that change in the data set is both the geometries and the material choices for those geometries.
And it turns out the printer also prints anisotropy into it. We didn't want that, but that's just how the printer works. So we also have different sample orientations.
Yeah, so it only prints in one direction. So there's a built-in anisotropy.
We have time for one more question. Oh, perfect.
Is the data available? Sign me up, first of all, for both challenges. And if the data is available and if there is an award for the winner.
I don't know what the award is. We haven't decided. But the data is just available, I think, as of this week. And so if you are interested in participating, then shoot us an email.
I'm interested to win it, not to just...
And then, yeah, good. That's the spirit. Yes. That's good. I think.
That's for the record. That was Karen who challenged. So it's on the record. Anybody else?
Yeah, shoot us an email, and then the data is available, and then I think we'll advertise it. But yeah, we'll share the GitHub. Yeah.
Michael, I'm coming over. Appreciate it. Thank you.
Sitting in a very inconvenient location. The issue I have is in the material modeling, is in extracting that from, say, whole breast. The challenges are having enough information to anchor that model. I mean, we can get into discussions of the proper invariance, and I want to get into all that. But the main issue I have is that because these models are so highly nonlinear and covariant, that's a very tricky problem, and you're sort of never going to get that in a clinical setting, which doesn't mean you can't use it, but there may be additional pieces of information you can bring in to restrict that form. And I think that's one of the big challenges of any kind of soft structure. We run into the same thing with our cell mechanics work and microvalve work and all the other stuff that we and a lot of other people do. And you really have to have a much more detailed knowledge of what's going on. You can't get it from just the forces and displacements of the bulk organ. I don't know if you have any comments on that.
I absolutely agree. I think this is sort of the extreme of the fully data-driven, and I think that's not to discount the very good work of making models that are microstructure based. And probably I think the optimal solution lies somewhere in the middle, where you can use information from the microstructure and some of these data-driven models in so a multi-fidelity way, for example. So I think that's probably the optimal, and then we kind of went all the way to one extreme. But yeah, I completely agree.
Awesome. I think we're exactly at time.